Hello, Math 2 Extended. This is Mrs. Bricky, and this lesson is for Unit 7. It's the third lesson on parabolas and graphing parabolas. Let's see, sorry. Okay, so a function that has a power of 2, like this one, y equals x squared, it's called a quadratic function. That's just the name of that type of function. And again, the thing that makes it a quadratic function is the power. So we're going to graph the most basic of these quadratic functions, which is the function y equals x squared. So each of our outputs here we will get by squaring the input. So -3 squared gives us 9, -2 squared gives us 4. And be mindful when you're squaring negatives, especially if you're using a calculator, that squaring means times it by itself. So -2 squared is a -2 that's multiplied by another -2. So when you square a negative number, you should be getting a positive result. -1 squared would give us +1. 0 squared would give us 0. 1 squared gives us 1. 2 squared gives us 4. So let's plot these points and see what shape we get for this graph. So if x is -3, the y value, the height is 9. If x is -2, the y value is 4. For -1, the y value is 1. Goes through the origin here, 1, 1, 2, 4, and maybe let's add one more value to our table. If we square 3, we get a 9. So this is a lot different from the other graphs that we've done lately. We've done lines and absolute value graphs. This one is not straight. It doesn't have straight edges the way the other graphs did. This graph is a curvy graph. And you've graphed exponential functions before that aren't straight, so you are familiar with this idea of curviness that can happen on a graph, but this is the first one we'll really look at this year. So this shape, a quadratic function has this shape, and this shape is called a parabola. So we're going to focus on graphing parabolas today. They're a little trickier to graph than lines or absolute values because of this curviness that they have, but I will show you how to get that curviness. Let's use a table to help us graph this one, and then after that, like absolute values, we'll start focusing more on the function. So if we substitute in, so we need to take our x values, subtract 2, square it, and subtract 5 from that. So our first one we're subbing in is -2. And you can use your calculator to evaluate these. Just make sure you get the parentheses in there. So this would be -2 minus 2 squared is -4, which squares gives us 16. 16 minus 5 gives us 11. So our first y value is 11. And then you'll sub in a -1. And so forth. Oops, sorry. Sorry. Oh, okay. Sorry. For -1, we get the value 4 when we calculate it. And we'll just keep going, substituting those numbers in. When we sub in 0, we end up with an output of -1. When we sub in +1, we end up with a -4. And sometimes when you first, if you're looking at table of values, sometimes it first looks like it's not going to work out. So I've got, the -2, 11, it won't fit on this coordinate plane. So I'll start with this -1, 4, 0, -1, 1, -4. And it kind of just looks like, how am I going to get a parabola out of this? But just keep going. If I sub in 2, I get -5. And if I sub in 3, I get -4. So this is kind of where it turned around, which is going to give us that U shape. And we could come up with or add some more values to our table. -1 would be our next Y value. and 5, the x value 5 would give us the y value 4. So you can see that parabola shape. Whoops. And the shape is called a parabola. Sometimes we'll say it's U-shaped, but the shape's name is parabola. Okay, so the vertex. So these parabolas have a vertex just like absolute value function has a vertex. It's that point where it turns around. And so when we start graphing these in a minute, we're going to focus on the fact that we can see evidence of the vertex in the equation. So we won't use a table of values all the time, but you can see that just like with an absolute value equation, the coordinates of that vertex are there present in the equation for us to sort of just inspect and find. So let's just talk about this curvy shape, because as we graph these, if we're going to use this idea of looking at the equation to find the vertex, we have to also know how to get the shape plotted. So this curved shape of the parabola is a result of the squaring process. So the perfect squares are 0 squared gives me 0, 1 squared gives me 1, 2 squared gives me 4, 3 squared gives me 9, 4 squared gives me 16. So this list of numbers right here are called perfect squares. So we want to think about perfect squares because parabolas come from squaring. So I want to think about how the perfect squares change. So to go from 0 to 1, I add 1. To go from 1 to 4, I add 3. To go from 4 to 9, I add 5. To go from 9 to 16, I add 7. So each time I'm adding the next odd number. And this is how parabolas grow. So at first, it grows up by a factor of 1. The next time, it grows by a factor of 3. And then last one on this graph is a 5, 1, 3, 5. So we often talk about parabolas having a 1, 3, 5 pattern. Now, of course, that pattern doesn't end with the 5. The next one would be 7, just like we have here on this chart. And then it would just be continuing with odd numbers. But usually for the purposes of sketching a graph, the 1, 3, 5 is enough. Now notice that each time I just went over 1. So we say we go up 1 over 1, up 3 over 1, up 5 over 1. And because the amount that we're going up is changing each time, it's giving it this curved shape. Parabola has that same shape on both sides. So when we're plotting these, after we graph out that right side, we'll just go back and graph out the left side. So these shapes are symmetric. It's like a mirror image on both sides of a vertical line. Parabolas are symmetric because if I square a number, it's the same as if I square the negative version of that number. So when I square a 2, I get 4. When I square a negative 2, I get that same number. So that's where the symmetry of the parabola comes from, is the idea that squaring is the same for both a positive input and its negative equivalent input. All right, so we're going to graph these by focusing on their vertex. So we'll plot the vertex first by inspecting the equation to find the h and k value of the vertex. And then we will use our pattern, which could be stretched, and we'll talk about that in a second, but we'll use that pattern to plot the curved sides of the parabola. All right, so here's our first one. So we inspect this equation to find the vertex. We see that our h value is 2 and our k value is 1. So remember that minus here, it does not come down to the vertex. We see a sign change with our h value. So we're going to plot the point 2, 1. And the stretch factor of this is just a regular parabola, stretch factor 1. So we're going to use a 1, 3, 5 pattern to graph it. So up 1 over 1, up 3 over 1, and in theory up 5 over 1, but that doesn't fit on our coordinate plane, so we don't need to draw it. So here's our, oh geez, that's like one of the worst parabolas I've ever drawn. Here's our parabola. Wow, sorry. We would say that this parabola opens upward, and it has, because it's opening upward, we have this lowest value, this minimum value of 1. All right, let's try another one. So for this one, if you are looking at your paper, I think it has a +4 or something over here. Just cross that off. I'm sorry about that. I just want to graph what I have on my screen, which is negative x plus 3 squared. So our vertex on this one, if you think about, this form of the equation right here, we have a 0. We're not adding any constants at the end of that function. So our vertex is going to be at -3, 0, which is right here. The negative here is what we call our stretch factor. So what that means, when you have a stretch factor, our basic parabola pattern is a 1, a 3, and a 5. If it's stretched, that's a multiplier. So we're going to take that 1, 3, 5 pattern and we're going to stretch it or multiply it by a -1. So what we're going to end up graphing for this graph is -1, -3, -5. In other words, this parabola is going to go down. So we're going to count down 1 over 1, down 3 over 1, down 5 over 1. And then, of course, the symmetric left side over here. And so this is what's called a downward opening parabola. And you'll see a parabola opening downward anytime it has a negative stretch. So this one opens downward. When a parabola opens downward, it has a maximum value, and this parabola has a maximum value of 0. So remember, when we talk about mins and maxes, we're talking about y values, and this is a y value of 0. Okay, this parabola right here, -2x squared plus 5, this is the one that is, for most students, the hardest one to identify the vertex, because the form of this equation is decently different from our generic form. We don't see parentheses here. We just see a -2 and an x squared. Well, the vertex does not involve the -2. The -2 is our stretch. So I'm going to write this equation just using our basic form to help you see what the vertex is. So the -2 is the stretch. The +5 over at the end is definitely our k value. And we've got an x that's being squared, and there's just not a number being added or subtracted from that x as it's being squared. So because that number is 0, we don't need to show it. So it just becomes an x that's squared. And because the only thing that's being squared is the x, the parentheses around the x become unnecessary. So that's why it just becomes this -2x squared. We definitely have the -2 in front of it that's multiplying it, but this whole part of it right here can just be written as an x squared. We don't need the -0. We don't need the parentheses. So because it's so much different looking than the parent function or the general function, sometimes people have a hard time identifying the vertex. But our vertex is at 0, 5 right here. So the stretch factor of this parabola is -2. So remember that the stretch factor is a multiplier. So we're going to take that -2 and multiply it by our 1, 3, 5 pattern. So the 1 becomes a -2. The 3 multiplies by -2 to give us -6. And the 5 multiplies by -2 to give us -10. So our pattern is that we're going to go down 2 over 1, down 6 over 1, down 10 over 1. Down 2, down 6, and rarely can we ever actually fit the down 10 on our graph that we're doing, because on paper we usually just don't have a coordinate plane that's big enough to be going down 10 units. So we end up with this, you might say skinnier, I guess, parabola, because it's stretched and it's like so much taller, it ends up looking kind of skinny. This one opens downward, which means it has a maximum value, which on the graph we can see is at the value y value 5. The domain of a parabola is all real numbers. So you can write it, the domain, as negative infinity to positive infinity, or if you prefer, you can use that symbol for all real numbers. Sometimes people look at these graphs and they're like, how is that all real numbers? It's so skinny. Like on my coordinate plane, I see that it's only between the -3 and the +3. But remember, these are arrows going off to the side, and I can sub into this function an x value as large as I want. I could sub in 1,000 and I would still get an output. It's just that the output is enormous, so it's just definitely not going to fit on this graph. But as far as like x values that are valid for this function, I can definitely substitute any number, no matter how large, no matter how small. It's just that it's not going to fit on my coordinate plane. Like this is my y value if my x value is 1,000. So definitely that point exists, just not on our coordinate plane, or probably on any coordinate plane that's on paper, because it's such an enormous number. So the domain, even though they sometimes look like the domain is limited, the domain of these is not limited. The range is not all real numbers. You can see that it has a maximum value, so the range is from negative infinity up to 5. 5 is the vertex, and that vertex is definitely part of the parabola, so we would use a bracket to include it. All right, one more graph. This one is 2 times x minus 4 squared minus 6. So our vertex is going to be at 4, -6. Our stretch factor is 2, which means the pattern that we're going to use is that 1, 3, 5 pattern that has been multiplied by 2 or doubled. So we're going to use a 2 and a 6 and a 10. And probably the 10 isn't going to fit. Up 2 over 1. Notice each time, even if the vertical stretch factor stretched that 1, 3, 5 pattern, I'm still just going over 1 each time. So up 2 over 1, up 6 over 1, up 10 over 1. And then we'll reflect that back to get the other side of the U shape. So this parabola definitely opens upward, which means it has a minimum value, which for this function is -6. Our domain is all real numbers. And our range this time starts at a number value, which would be -6 for this function, and it goes up to infinity. So your range on your parabolas and your absolute value functions always looks like one of these two. It's either from negative infinity up to the max, or from that minimum up to infinity. Okay, we're now going to just do that process backwards. If I give you a picture of the graph of the function, can you write its equation? So you want to start by identifying the vertex. For this function, the vertex is the point 3, 1. And then you want to look for and try to decide if it has been stretched out. So I would always kind of check, does it go up 1 over 1? And you can see that this parabola does not go up 1 over 1. So it has some kind of stretch to it. In this case, look for another nice point. It looks like right here, up 2 over 1, up 6 over 1. So our stretch factor is 2, because our pattern is 2, 6, and it probably would be 10 if we could see it. So our equation is going to be, you can use f of x or you can use y. F of x equals our stretch of 2, and it's going to be x minus 3. Don't forget the power of 2. Sometimes, especially at first, people sometimes forget that power. But the power of 2 is what makes it that U shape. and then plus 1 for our k value. So this is our equation of our parabola. The domain is negative infinity to positive infinity. This time our range, our lowest value is 1, and it goes up to infinity. Okay, so I want to review and just practice, get another chance to practice intervals of increase and decrease with this parabola. Remember, intervals of increase and decrease are related to domain. So we know the domain of this function is from negative infinity to positive infinity. We just need to break that up into, is the function increasing or decreasing on each part. So if you think about this graph from left to right, first side is a decrease. So from the negative infinity over to that vertex of 3 is a decrease. And this negative infinity, remember, is an x value. Sometimes people are tempted to write a positive infinity because they're like, the function is way up high. But we're not talking about this value, this y value. We're talking about this x value over here, negative infinity. So that first part of the parabola is a decrease, and then once it hits the vertex, it turns around and it increases. So our domain from negative infinity to positive infinity is broken up into these two parts. So our increase starts at the vertex and goes to infinity. And again, it's this infinity that we're talking about. We're breaking up this domain. So together, that makes the whole domain of negative infinity to positive infinity. Okay, let's write this, this equation for this parabola. So identify your vertex. This one is at negative 4, 6. And our stretch factor, our pattern, looks like it's going down 1, down 3, down 5. So our stretch factor is negative 1. When we're writing an equation with a stretch factor of negative 1, you don't need to put the 1. It's okay if you do put the 1, but it's definitely not necessary to have the 1 there. We just need that negative symbol, and that's good enough. Okay, so we've got, let's see, x, and this is going to be a plus 4 because we have an x minus a negative 4. So that ends up being an x plus 4 in our equation, and then plus 6 over at the end. So this is the equation of this graph. The domain is, of course, negative infinity to positive infinity. The range for this graph would be, whoops, I started doing a bracket, but this is definitely negative infinity up to 6. So for increase and decrease, we need to break that parabola up. When we look at this one, we can see that it's increasing at first, and then when it hits that vertex, it turns around and it decreases. So we've got a little bit of each, a little bit of increase and a little bit of decrease. Our increase is happening from the x value negative infinity to the x value negative 4. And then once it hits that x value of negative 4, it turns around and it goes down, it decreases. So you can see if you put those two pieces together, whoops, parenthesis, that covers the entire domain. Okay, so last one, I think. Yeah, last one of these graphs. Use the graph of the function to give the following. So we want to know, does this function have a maximum or minimum value? And you can see that it does not have a highest value. We've got arrows going off to the top, but it does have a lowest value as a minimum value of negative 9. The x-intercepts, we haven't done a lot with intercepts this year. The x-intercepts on the graph, we can see it has 2. Remember, parabolas are symmetric, so they often have 2 x-intercepts, though they don't have to. I'll let you think about when they might not have 2, but this one definitely has 2 x-intercepts. I'm fine if you just list the x-intercepts with a comma separating them. The other option would be to list the entire points. But if it has asked you for an x-intercept, I am fine if you just list the x values of the x-intercept. The y-intercept, make sure when you're looking for the y-intercept that you aren't looking for the vertex necessarily, I mean, it could be the vertex, but it's not necessarily the vertex. So the x-intercept is right here. I'm sorry, the y-intercept is right here at -8. Okay, it asks us to find f of -2. So this -2 is an x value on the graph, and we are looking for what is the height of the graph for that x value. So we can see it's down here. So this one is also -8. Symmetric, so it hits that height of -8 twice. Our next question says, find x when f of x is equal to -5. So this is telling us a y value of -5. Here's the height of -5 right here. We definitely have an x value of 1. Parabolas are symmetric, so make sure you always check to see if you can find the other one. Our other x value is -3. And again, you can separate those with a comma. But there's definitely two x values for which the function has a height of -5. The last thing asks for the line of symmetry. So remember, we talked about that these are symmetric. The line of symmetry would be like the mirror that cuts that parabola into those two sides that are mirror image of each other. So the line of symmetry is a vertical line, and so our equation will look like x equals a number, and for this parabola, that line of symmetry is x equals -1. Okay, last thing, we want to just write the equation of this really quickly. The vertex is at -1, -9, and it just has a regular 1, 3, 5 pattern to it. So our equation would be x plus 1 squared. So remember, our vertex is at -1, -9, and then -9. So we see an x plus 1 in the equation. All right, there's the equation. Okay, the last little thing I want to talk about is transformations. Often we think about these parabolas or absolute values that we are graphing. So sorry, we have two families of functions now. We have the parabola family and the absolute value function. And we often think about these functions compared to what we call their parent function, which would be the one that has the vertex at the origin. And so what we sometimes do is we think about these things as being a transformation or a shift. So if this is my parent function, my base function at the origin 0, 0, I could think about this parabola as having been shifted to the left h units and up k units. So we think about these transformations. And if my base absolute value function was this one, I could think about this new one that I have on my screen as having been shifted to the right by h units and down k units. So we think about our h value as our left or right translation and our k value as our vertical translation. And then our stretch, our a value, is a vertical stretch. So we want to just describe the horizontal and vertical translations that these functions have undergone. The horizontal ones are kind of tricky because of the weird sign change that happens. So one of the best ways to be successful with these is just to write down the vertex. So in this case, and I'm going to draw a graph for this one, but I won't after that. In this case, our base function is at 0, 0, and this function's vertex, f of x, is at 1, 4. It's up here. So the translation that happened in moving my little parabola from the vertex at the origin to the vertex right here is that it went over 1 unit and up 4 units. So it moved to the right by 1 unit and it moved up by 4 units. And again, I really just encourage you to write down the vertex of your functions and see if that helps you to get the left and the right correct. The up and down isn't so hard as the left and the right. So for this function, our vertex would be at -6, 0. So the horizontal translation is that it went left 6 and it didn't go up or down. And again, if we had a little graph, we could think about that. So here's where a basic absolute value function is, the parent function. This one has a vertex at, whoops, oh my goodness, sorry. This one has a vertex at -6, 0. So you can see it didn't move up or down. So we would say it has no vertical translation. Okay, our last one, the vertex of this parabola is at 0, -10. This is one of those tricky ones that has an x coordinate of 0 for the vertex. It's like this. So we don't see the parentheses. We do still see the power, of course, because the power is what makes it a parabola, but we don't see that 0. We don't see the parentheses. So it's hard sometimes to remember that one. So if our vertex is at 0, -10, that means this function did not move left or right. It simply moved down 10 units. So again, our base parabola would be here, and this one moved just down 10 units. It didn't move to the left or right. Okay, last one. It says, given function f of x equals x plus 4 squared minus 3, create a new function g of x that is equivalent to function f shifted 8 units up. So we want to go up 8 units and 2 units to the right. So I encourage you to write down the vertex of these functions to help you. So the vertex of f is -4, -3. We can see that in its equation. We want to go up 8 units. So the 8 is going to be added to the y coordinate because that is in the y direction. And the 2 units to the right would be added to the x coordinate. Oh, I cannot spell coordinate. And it is moving to the right, so we would add 2 to that x coordinate. So that means the vertex of g, our new function, is going to be at -2, 5. So it asks us to create a function g of x, so that means to write its equation. So we would say that g of x is equal to x plus 2 squared plus 5. So we're just using that new vertex to write the function. Be careful. You can probably see the 5 pretty easily where the 5 shows up, but the x direction is always a little trickier because of the sign changes and things. So if you write the vertex down, you'll get it right. All right, that's it for this video. Thank you for watching. If you have any questions, let me know. Thanks.